Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on November 20th, 2025, about 3 days ago. It introduces a new evolution strategies algorithm called EGGROLL that replaces huge full-rank noise with tiny low-rank factors, delivering up to a hundredfold increase in training throughput for billion-parameter models, while staying almost as fast as pure batched inference. The paper is titled Evolution Strategies at the Hyperscale. And as we will see later, the implications for training large, even non-differentiable models are pretty significant. Alright, Figure 1 gives a cartoon of how EGGROLL turns many tiny low-rank tweaks into one big weight update. The green block on the left represents the initial weight matrix for the neural network layer. In the center, each worker forms a rank 1 perturbation, which means an outer product of a skinny column and a skinny row for that worker. These perturbed weights go through the task to get a fitness score, so better performers receive larger weights in the average. The bell-shaped curve then shows a weighted combination of all perturbations that produces the final high-rank update on the right. Figure 2 moves from the schematic to hard numbers. Panel A shows normalized training speed, where pure inference is 100, and EGGROLL reaches about 91, far ahead of proximal policy optimization at roughly 34, and OpenES at essentially 0, so the new method runs almost as fast as plain inference. Panel B tracks test loss for integer-only recurrent language models, and larger population sizes give clearly lower final loss curves, which means better models when more workers explore in parallel. Alright, Figure 3 digs into why the low-rank trick stays accurate. The curves show the marginal density times score, P of Zij, times Zij, for different ranks R, and they converge onto the black dashed Gaussian limit curve as R grows. Even R equal 1 already roughly matches the shape, and by R around 10, the colored lines almost overlap the limit. This rapid convergence supports the theory that EGGROLL's gradient estimate is very close to true Gaussian evolution strategies, even at very low rank. So Figure 4 shifts from theory to reinforcement learning results. The panels plot normalized return versus training steps, with the dashed line marking proximal policy optimization performance. EGGROLL in dark blue generally matches or exceeds OpenES in pink, and sometimes approaches the proximal policy optimization level. Some tasks like Jumanji 2048 show both evolution strategies closing in on proximal policy optimization, while others like Kinetics Thrust Control Left strongly favor EGGROLL. These curves support the claim that low-rank evolution strategies remain competitive, with strong gradient-based baselines across diverse environments. Alright, Figure 5 shifts to language model reasoning tasks. The left panel shows countdown, where the purple EGGROLL curves climb to around 35% validation accuracy, clearly above the pink GRPO curves at roughly 23% for the same wall clock time. The right panel tracks GSM 8K, and EGGROLL again rises higher and stays higher throughout training. These gains come because EGGROLL evaluates vastly more parallel generations per graphics card, so evolution strategies search the space much more efficiently. So while Figure 5 highlighted downstream performance, Table 1 spells out how the evolution strategies baselines were tuned. The table lists population size, number of parallel evaluations, and the low rank setting, which together control how many candidate models run in each wave. It also shows optimizer choice, learning rate and decay, and the noise scale sigma with its decay, plus whether to use rank-based weighting and deterministic policies. These ranges define a shared, carefully searched budget, so speed comparisons stay fair. So the big message is that EGGROLL makes evolution strategies practical at hyperscale by turning costly, full-rank noise into cheap, low-rank factors while keeping performance on par with strong gradient-based methods. This opens a path to training huge, even non-differentiable or integer-only models without backpropagation. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.